Hello, my name is Rotak Pudworthan,
Hello, this is Arsh Patel.
and this is our solar cell project to determine the internal resistance function. So, first we need to address what actually is a solar cell. Well, a solar cell is a device that is capable of converting light into electricity. And so the sun will emit energy in different wavelengths in the visible spectrum, and solar cells have a band gap which dictates the wavelength of light they can actually absorb. The other waves are either reflected or will pass through. So, the semiconductive part of the solar cell is the active part, and it is the balance between conductors and insulators. This part allows for the electrons to be excited. The semiconductive layer has a top layer. This layer is negative or considered n-type, which is the conductive part. The bottom layer is made up of an element that has fewer electrons than silicon typically, which gives it less electrons that are free to move. So it is p-type and less conductive. As light enters, there are holes in the center where an excess positive will move downward into the p-type, and the electron will go up into the n-type. By this logic, it will allow electrons to flow. This is how current is generated by the solar cell.
Solar cell heats up because of a number of reasons. One, it only absorbs certain wavelengths of light, so the rest is reflected as heat. Two, the photovoltaic effect causes energy to be released as heat. And three, energy is dissipated as heat due to Joule's law for the internal resistance of the cell, which states that P is equal to I squared R. The heating up of the solar cell is what causes the internal resistance to vary with time. Our objective in this experiment is to develop a mathematical relationship to express the internal resistance as a function of time. Let's use the circuit we have on the screen, with the solar cell functioning as a battery with an internal resistance in addition to a load resistor. Real voltage across the solar cell is equal to the ideal voltage minus the product of the current and the internal resistance. A true fact is that the EMF is constant at all times in the circuit, which can be justified through energy conservation and Kirchhoff's loop rule. Now let's substitute the previous expression to get the voltage across the load resistor, real voltage, current in the circuit, and the internal resistance at times 1 and 2. Solving for internal resistance, we receive this expression. It's important to note that the internal resistance at times 1 and 2 are not the same. We are storing them in the same variable since this variable is a function with respect to time, not a specific value. You can rewrite the average rate of change formula for the voltage with respect to current as the derivative of voltage with respect to current. Since both voltage and current vary with time, we can rewrite the internal resistance derivative as a parametric first derivative with respect to time. Finally, since we are only interested in the magnitude of internal resistance, we can take the absolute value to arrive at our final function. This function will be used as the baseline for our experiment.
Alright, so our setup was between Mr. Bushka and Mr. Lee's classroom so that we can keep the room dark. This is so that the light sensor only picks up on the light from the light bulb itself, and thus provides the light intensity of the light bulb. You can see Arsh putting some books down, the solar cell, and he's grabbing some rulers as well. The books is to provide a vertical offset of about 4 inches. This way, the solar cell lines up with the light bulb. The rulers are really important because it maintains a fixed distance of 6 inches, and a second ruler is necessary for the light sensor. At the end, we move the light bulb down to the second ruler and measure the light intensity with a light sensor based on that. Alright, so here you can see Arsh lining up the lamp with the ruler, and one major flaw I want to go over is using a 390 ohm resistor because its resistance was way too high, so we couldn't measure any current in our Pascal capstone data, but once we switched to a 10 ohm resistor, that was fixed. And here you can see our lamp is on and we're collecting data. And then we move the lamp over to the sensor to calculate the light intensity.
We use the ammeter and voltmeter to receive the following data for voltage versus time and current versus time. We also use the light sensor to obtain the value of the light intensity in our experiment. We first graphed voltage versus time in Google Sheets, and because there was a considerable variance, we were able to get the following third-degree polynomial as a trend line for our data. We then graphed current versus time in Google Sheets. However, because the current did not change much over the 430-second interval of data collection, we had to select specific points to receive the following third-degree polynomial as a trend line for our data. Going back to this equation we derived, we take the first derivative of each function and the quotient to finally get our internal resistance function with respect to time.
Since function is restricted to our interval of data collection though, since both the voltage and current functions do not reflect the actual values in the solar cell as time goes to infinity, and it is bounded to our specific time intervals. Taking a closer look, we see that the internal resistance function decreases by a factor of 10 over the interval, meaning that heat has a non-negligible impact. Thanks for watching.